Yeah, so this is work I've done with Graeme Slater at the University of Chicago. I'm going to start by telling you something I probably don't need to convince you that we really want fossils in our phylogenies, or we could get the wrong answers about things like diversification, trait evolution, or biogeography. But there's a challenge in generating these trees, and that's really what this talk is going to be about. So what we wanted to do is, our goal was basically threefold. We wanted to include every single cetacean species, extinct or extant. We wanted our output to be a timescale tree, because that's what we need for macroevolution. And then the more nebulous one is we wanted it to be a good result in whatever that means, and so I'm going to call it truthiness. So the size of the problem then is we've got something like 101 living species. This is almost certainly an overestimate, and we're going to revise this down a bit, but most of our diversity is in extinct species, which is obviously what we're used to working with as paleontologists. So normally we'd want to use total evidence as a way of solving this, the kinds of things that Robin talks about, but that's not going to work for cetaceans, and it's not going to work because the morphological challenge is too great for us. So here's a collector curve of cetacean species from Linnaeus on the left, all the way to the present day on the right. Here's 3,000 cladistic datasets scored by their taxon counts. Here's just the ones that focus on cetaceans, and you'll see we've basically got nowhere near covering the kind of size of data set we need here. And if we fit models to extrapolate these lines off into the future, they're not going to converge anytime soon. So this means our only real solution to this problem is to use synthetic topologies, which is basically getting small trees and putting them together to make a big tree. So we have three sort of main options to do this. So the first is an informal supertree. So normally there we take some limited number of phylogenies that already exist, digitize them, and then often in some opaque way sort of cut and paste those together. And then we get a tree out at the end that sort of doesn't often deal with phylogenetic uncertainty very well. Maybe there are some polytomies in there. An alternative to that is a formal supertree approach, where it's normally a broader sample of trees. There's an explicit algorithm that allows us to unite them together. And then we get phylogenetic uncertainty in our sample that we get out at the other end. We're not going to use either of these. What we used instead is a meta-tree approach, very similar to a formal supertree, but what you stick in at the beginning isn't trees, but the data matrices used to produce them. So Katie promised I would bash supertrees as a way of justifying this, so I'll do that now. So if you're doing a supertree, you're stuck with the published figure. Here's an example from a paper by Felix Marx. This is the tree you get in the paper. This is the tree you get if you reanalyze the matrix. So what he did for his paper is collapsed a lot of his non-focal clades. That's information you lose if you use the supertree that you can retain if you do a meta-tree. Here's a more complex figure. This is a strict consensus tree, number of possible bifurcating resolutions against the number of trees actually used to produce it. Nothing really falls out on that one-to-one line, which is basically telling us when we produce a consensus tree, we're losing information we can't get back. Supertrees are often stuck with this consensus tree. Meta-tree, we can keep the original data, keep more of the phylogenetic information. So this basically leaves us with a pipeline we can apply to pretty much any data set we want. So we shove our matrices in at the beginning. We do taxonomic reconciliation to make sure that all of those OTUs match up. We then add in a taxonomy tree. We can filter the data and weight it to deal with problems of redundancy between data sets. We can then do a matrix representation of that, as Neil talked about earlier and Katie talked about yesterday. Then we can take a bite out of that using safe taxonomic reduction to decrease the sample size we need to work with. And then we get our tree out at the other end. So I went through that very fast, so now I'll go through it in a bit more detail. So I've been building a large database now of cladistic matrices. There's 3,000 data sets there. If you go on my website, you can find some of them. There'll be references here with a bunch of links underneath. This includes the data in sort of various formats, the trees we got up from reanalyzing them. And then at the end is our XML file that deals with metadata and, more importantly, the sort of taxonomic reconciliation side of things. So what this means is basically taking whatever we have as OTU names in our data sets, whittling them down to a set of valid species. So this is really where the labor comes in. This has to be done super carefully. I'm going to show you a negative example of this. This is an actual published supertree. I'm not going to label the authors, but just to show you a problem with it. Here's a clade of 3 taxa, 2 rhynchocephalians and a squamate. The authors have then assigned all of this to squamata. Rhynchocephalians are not squamates. The real clade that unites squamates and rhynchocephalians is Lepidosauromorpha, which is a separate OTU down here. So this is a failure of taxonomic reconciliation that results in a tree we cannot use for anything. I'm going to do this now. There we go. So we need a single true taxonomy to its Gordian knot. To do this, so we're using the Palaeontology database. Generally, you should be very cautious about doing this, but cetaceans are really awesome, and they're really awesome because of Mark Ewan. So that made our lives a lot easier. We also include a taxonomy tree in the data set. The reason why we do this is to deal with that issue Katie raised of rogue taxa. So you've got some basic information about where something should go. But this is not a constraint, and it's heavily down-weighted. It never gets to say over phylogeny in the resulting data set. But we're also going to use this later to reinsert taxa that aren't otherwise sampled. So another issue is filtering in the data set. So what we're used to seeing, and you'll all be familiar with this, is someone will come up with a matrix. Some other people will reuse that matrix, some other people will reuse the matrix will reuse that matrix, and so on. So we have to deal with this redundancy, non-independence between our data sets. Normally what this means is these reused data sets become basically redundant, so we can get rid of those, but what's left is not independent. So that's where we would deal with that with things like weighting. So the next step to sort of make it a bit easier is apply safe taxonomic reduction. So this normally does it's really useful with matrix representations. It almost always reduces the solution space you have to search in its size. And then at the end, you get a tree out of this. So this is our first attempt at cetacean trees. This is the largest tree ever produced for cetaceans, as far as we know, 381 species. But actually, if we return to our goals, it's not quite getting us where we want to go. So first of all, we wanted total taxonomic coverage. We're around 300 species short with this tree. We want it to be timescaled. This one is, but in a horrible sort of post-hoc way instead of the nicer probabilistic ways we have access to now. And it's also not ideal in our truthiness. There's some strange relationships among the extant species that we wouldn't really believe if we were thinking in a sort of molecular way about these things. Again, apologies to Rob Asher, I suppose. So how can we deal with these problems? So the first one is taxonomic coverage. So let's imagine we're producing an Euler plot for our data. So we have a circle representing the size of the species in our tree, another one representing all the possible species. If we did an ideal Euler plot, these two circles would be the same size, they'd perfectly overlap. That's not what we see with the data. So this is our sort of basic approach, and this is a slightly updated data set. So we've got 434 species in here. And that's where we're only including species if they're sampled in one of our source data sets. We can go sort of a bit further by saying, well, if the genus is sampled, we can assign the species in just to that genus. That gets us to 577, but it's, again, not all the way where we want to go. So the only way to do that is to shove everything in effectively, and that gets us to 720. So if you're paying attention, that's more cetaceans than there are cetaceans. So you might wonder why that is, and you can also see that red circle is creeping out of the yellow circle. So to give you a sort of a very much cherry-picked example of what these things are, these are specimen level OTUs that nobody's given a valid name to. So here's an example of one that's appeared in a few of our source trees, but actually recently this has been given a name, so it's moved into that middle area. And so more generally, this is what happens with these kind of OTUs, so our preference is to retain them. The bad stuff is normally actually in this other section, so it's taxa that have never been included in a phylogeny. Again, this is a cherry-picked example. Basically, it's a taxon named almost 200 years ago based on an isolated vertebra that's not very diagnostic, and the specimen has since been lost. So because we've got these different things to deal with, we've decided to retain these three different taxonomic levels for the moment and sort of see what they give us, and then we're going to make a choice later on of which one we really want to do. So with the safe taxonomic reduction, it's worth pointing out this. Basically, these data sets are all the same in terms of computation time cost once we apply this algorithm, which is why it's always worth doing with these types of data sets. So the next issue is with time scaling. So we wanted to use probabilistic approaches. So we're going to use BEAST2 here. And what we're doing then is inserting three different pieces of information. So the strict consensus that comes out of our meta-tree pipeline. We've got some molecular data in now coming in from a published alignment of all the living species. And then we've got the ages of our tips as well. So we're using three different pieces of information to get us to timescale trees. And then that final truthiness, we can also reuse that matrix to basically turn all of our input data sets into miniature total evidence data sets. So what that means is we've taken our meta-tree pipeline and done a sort of version 2.0. So we've included our alignment at the beginning, so we're shoving molecular information now into the beginning of the data set. We've got this option to include more taxa by modifying our taxonomy tree, and then we've bolted an extra block on the end effectively to get us to probabilistically timescale trees. So some very early results from this, what we did is a kind of attempt at tree space. So we took from our various different pipelines that we now have, whether or not we include molecular data, what level of taxonomic coverage we want. We stripped those down to a random sample of 100 trees, threw away everything that wasn't extant, and then did sort of tree-to-tree distances between everything that was left, and then sort of forced them into two axes of variance in this space here. So if we look at just the morphological pipelines, first of all, we can see that we're really sampling 3 different tree islands in tree space with our morphological data. But unfortunately, they are not very close to the molecular hypothesis that we get if we just basically inferred a tree from our alignment on its own. So our hope then was that once we included our alignment in the pipeline, we'd migrate towards this, but as the axes of this graph are sort of spoiling, that's not what happens. We actually end up with trees that are equally incongruent with the molecular hypothesis, but in a very different way. But we see we're sampling a much smaller area of tree space once we've basically increased our precision, if not our truthiness, with this data. So I can't talk too much about the rest of the results, but here's one of the probabilistic timescale trees, so a new largest ever tree of cetaceans. This is actually one of our smaller ones, so this is only the species one, not the genus one or the everything one. So we still need to do some improvements to get this towards where we'd be happy publishing it. So the first of those is dealing with some of those final issues with taxonomy, getting rid of things that are named from a vertebra that's not very diagnostic, reducing our extant species count. We've basically got these 6 different pipelines, and the other thing is to try and sort of turn this truthiness concept into something more rigorous in terms of quantitative measures. And that's where I'm going to finish. Thank you.